Welcome to this next seminar in the SIAM series of the Activity Group for Financial Mathematics and Engineering. As usual, to the audience, if you would like to ask any questions or have any comments, please write them in the chat, and then I will notify Carole, and she will then respond to these questions and comments. And yeah, so and then I would like to introduce our speaker today. Carole Bernard is our today's speaker. It's a pleasure to have you here, Carole, tonight. Carole is a professor at the Grenoble Ecole de Management and also at the VUB. And she is well known for her work in finance and actuarial science and general quantitative economics. And today she will be speaking on a topic on portfolio choice. And so the title of the talk is Multivariate Portfolio Choice via Quantiles. So the screen is yours, Carole. Thank you.
Thank you. Thanks a lot for the nice introduction. And yes, do not hesitate to interrupt or to tell me if the sound is not good or you cannot follow, or if there's a problem. I will try to fix what I can. Or to explain if it's a problem on understanding something. So this talk is actually a joint work. Oops. Oh. Yeah, this talk is a joint work with several people. In fact, it started with a joint work with a former PhD student, Luca De Janeiro, and Steven van der Velde on optimal multivariate financial decision making. And I was presenting this paper, and then we started an extension and a link with some quantile formulation of an optimal portfolio that I did with that I started with Andrea Perciaso, who's a PhD student in VUB, and also with Steven van der Velde, who's co-supervising the PhD thesis. So I'll be talking on optimal financial decision making, and I'll go back to cost efficiency. I apologize for people who really are familiar with cost efficiency, if any of you are familiar with this, because it will be maybe sound too easy. But then if you really understand the univariate case and why cost efficiency is an important point when you want to choose a portfolio, then the generalization to the multivariate case is actually very easy to understand and natural. The proof is actually not more difficult, and even though we move to the multivariate case. Then I'll explain how, I will need for portfolio choice in a multivariate setting, the notion of multivariate cost efficiency, and I'll explain how actually this is a notion that is very easy to obtain, at least numerically. And in some cases, in theory, we can do it, but like in the multivariate normal case, which I will use as an example, but this is the only case where actually I can solve for multivariate cost-efficient strategies explicitly. And then I'll explain, in fact, where it can be useful. And there are several places which it goes back to the literature on optimal risk sharing. So I'll explain the link with multivariate risk sharing and how to use the quantile formulation that was developed in a univariate case to solve this multivariate problem. And finally, I hope to have some time just to discuss a few open questions on multivariate preferences by trying to, like, we came up with the results from the talk, essentially by thinking about multivariate preferences and how, like, what are good criteria to take a decision in a multivariate setting. And we hope that this actually approach can help further in this direction, but there's still a lot of open questions. So the last section is more about questions than solutions, actually. So just to give a bit of credit, this is actually a work that builds on a lot of different literature, and it's not necessarily very like each piece I find is not so difficult, but it comes from different area of research, and it's about also linking these different areas. So there's all the literature on cost efficiency and quantile formulation of portfolio selection, particularly the work of Dybvig and He and Zhou, who have a paper with very similar title, Portfolio Choice via Quantiles. it also, as I said at the end, it was motivated, in fact, by trying to explain how to make a decision when you have several variables that you want to put in your optimization. So multivariate preferences. So there are works that have been done more in economics, and also a few on the multivariate utility maximization, especially this one, which is the finance one. And then it's also linked, or at least I'm going to show you the link with multivariate optimal risk sharing. And this goes back to the original problem of Borg in 1962, and that has several extensions and it's really not an exhaustive list. I put a few people you may know, but there are many more who have worked on optimal risk sharing. And I've also mentioned, in fact, on optimal risk sharing, there's like the inf-convolution, the sub-convolution, but there's also some work that is beyond expected utility and is relatively new, where risk sharing is based on quantile. I mentioned these two papers of Embrecht, Zhou, and Wang, because this is actually the only example I know where the problem is solved explicitly and does not lead to comonotonicity. So this is a concept that will come back in the paper and in the talk, is that in general, when you optimize things and multivariate optimal risk sharing, all these papers, for instance, all are about why the optimum at the optimum, x1, x2, xd, if you're in d dimension, they are all moving in the same direction in an optimal risk sharing. They are all comonotonic. And this is, in fact, the few papers, with also the paper of Weber, where they talk about optimal risk sharing, which is not a comonotonic way of sharing wealth. Then there are a few papers on cooperative investments that are a little bit more finance related, and the last one on systemic risk, which is more about modeling. Also, it's an example, in fact, of relevant example where you have a regulator who tries to model as preferences on a d-dimensional system, which is the system of banks, for instance, and has some objective function relative to this d-dimensional system. So if your paper is not there, I apologize. You can still email me to add it, but in the paper there are more references, and it's really not exhaustive. Just to tell you that this is related to many areas, and so maybe some of you like recognize like they have done some work in one of these areas. So let's go to explain, in fact, the first concept that will be the key in the paper, which is the cost efficiency. So a portfolio is going to be cost efficient, or I'm going to say it's cost efficient, if it has a distribution F that I cannot obtain with another portfolio that is cheaper. So if you have all portfolios that have this distribution, the one that is cost efficient is the one that is the cheapest among all these portfolios. And the setting I take is the setting of a complete market. So I have one pricing kernel. You could use the expectation under Q to price, but what I do, and because then I will have preferences and a portfolio problem, and everything it will be optimized under the real world probability measure. You maximize your utility under the real world probability measure. You minimize your risk under the real world probability measure. So because I need the two in my optimization, it's easier actually to work with the real world probability measure. So the expectation that is here is actually the real world probability expectation. And so the Xi is just the Radon-Nikodym derivative that gives you the change of measure between P and Q. And so this can be also interpreted as an expectation under Q of XT, or the stochastic discount kernel Xi, which is also state price density that I will use throughout the paper, in fact, to explain how I compute the cost. So this is the optimization I'm solving, the expectation of Xi XT, which is the cost today of receiving XT in the future. And I'm trying to find the strategy that has the cheapest cost and generates the distribution F. There's no arbitrage here. Just think of a digital option that pays when the stock price goes up, another one when the stock price goes down. and you take the threshold where there's half-half probability to go up and down, they have half-half probability in the real world to go up and down, but the risk total probability will be different, and so the prices will be different, and one will be cheaper than the other. So we're really looking for cheapest in the price, and the distribution that is here is the real world probability distribution. This problem is actually very easy to solve. You look for a distribution, you look for a payoff, and we are in a complete market. So any final payoff, there is a replication strategy that allows to get this final payoff. So I'm looking just at the terminal wealth, this terminal payoff. It has distribution F, so I can write it as F minus 1 of the uniform. Anything that has distribution F can be written this way. So I just need to know which uniform will actually give me the cheapest, the cost-efficient way. And this is also easy to find if you note that the price of it is the expectation of the product. So it's related to the covariance or the correlation between the pricing kernel, Xi, and your payoff xt. And so if you look in this, in the left side here, you have the cost of the payoff minus its expectation under P, mu F, and the expectation of the pricing kernel, the standard deviation of the pricing kernel, and the standard deviation of F. Everything is fixed except for all these payoffs that have distribution F. The only thing that is not fixed is the price, expectation of Xi xt. So minimizing the price is the same as minimizing the correlation. And then if you assume Xi is continuously distributed, which I also do in the paper to simplify everything, you have actually that the cost-efficient payoff is unique and can be written this way. So this is the unique way to have minimum correlation with the pricing kernel. So you have a uniform distribution because you apply Fxi of Xi. So this is the CDF of Xi that you apply on Xi. 1 minus u is the uniform, and this is the only uniform that is decreasing in Xi, so that minimizes the correlation. So this is extremely easy problem to solve. Now, why is it interesting is that anytime you want to optimize your portfolio, you end up finding that your optimum must be cost efficient. The proof also is relatively simple, so I'll go through quickly. Is that is proof by contradiction. You take a payoff, you assume it's optimal, so you maximize the expected utility, but it's not cost efficient. So you can find something else with the same distribution that is cheaper. And if it has the same distribution, it has the same utility. So that's the law-invariant property of utility that I'm using. And if it's strictly cheaper, I can find this additional cash that I saved by investing in YT instead of XT star and invest it in the bank account. If I do that, I actually dominate strictly the utility of Y, and therefore I actually contradicts the fact that XT star is optimum, and thus it must be cost efficient. So we really have maximum utility, the optimum must be cost efficient. And what do we use? We use low invariant and increasing nets. So this is the two only properties that you need on your preferences, and you don't need expected utility there. You only need the fact that you're optimizing a preference function that has non-decreasing property and low invariant property. Equivalently, that means that V respects first order stochastic dominance. And in this case, all these optimal portfolio, if they exist, so in the case you have existence, the optimal portfolio is cost efficient. And therefore, it must, if you know its distribution, you can write it down as F minus 1 minus F psi of Xi. So if you understand this, then you see that the quantile approach for portfolio choice is very natural. So the idea is instead of optimizing over all possible payoffs that have the right budget, we know that the optimal solution have a very nice way to write. They are all of this type. They are written as F minus 1 of 1 minus F psi of Xi. And if they are written in this type, Xi is the market, is the pricing kernel. So this is given by the market. 1 minus F psi of Xi is given in the market. So the only unknown is F minus 1. So your problem that was an optimization of all possible random variable or all possible payoff in your financial market can be written, in fact, as a problem of searching a quantile function. And that is called like the quantile formulation of an optimal portfolio selection. So you see in one dimension, you get back this, this formulation. And then it allows to solve problems by, instead of solving for the optimal payoff, you actually solve for the optimal quantile function. So you optimize over the possible increasing functions and not anymore over all possible random variables. And that this is actually much easier and it can be done numerically. And this is one thing that we exploit afterwards. How to generalize this thing to multivariate? Then if you understood what happens in univariate case, you'll understand why in multivariate cases it's quite natural. So our multivariate setting is that we look at preferences that are d-dimensional. So I have a preference over x1, x2, xd. This could be the expected utility, or it could be something else. And I'm assuming I have a joint budget for x1, x2, xd that I need to allocate. So this is the sum of xi. And so my budget can be written as the expectation of xi sum of xi. And what do I assume? I'm assuming V is strictly increasing in at least one of the components, and also that is law invariant. And so what happens is, like, if you have two payoffs that have the same distribution, your value for V is the same. If you have increasingness in at least one of the D components, you're going to be able to do exactly the same trick by investing the cash amount in this, the cash that you save if the optimum is not cost efficient, in this dimension in which it's strictly increasing. So you will have exactly the same conclusion, that the optimal investment for an investor that maximizes a d-dimensional functional with a joint budget like this one must be cost efficient in this sense. It must minimize the total budget subject to a fixed distribution x1, x2, xd. And so the question now is, we characterize all these multivariate costs, like all the optimum for all these multivariate problems. So I'll go back here. Here, what was interesting is to say all the optimum are cost efficient, and the cost efficient strategies can be written this way. Once you can characterize how they write, then you can actually solve for them in a different way, at least looking for the quantile. Here, what we have is the multivariate cost efficiency problem, but then we still need to know how to solve this problem. And it turns out that it's numerically very easy to solve. And in theory, it's actually, I have to recognize I cannot solve it. Like, there's no formula like this f minus 1 minus f psi of psi t. You can't do that in this d-dimensional setting. So I don't have the closed form in d-dimension. But I can solve, for instance, the multivariate Gaussian case in explicit forms in a log normal market. So if I make assumption on psi t, I say it's log normal. I make assumption on the joint distribution G, and then I can actually solve it explicitly. So why numerically it's actually easy? The observation is that we need to solve this problem. Minimum costs of the total budget, like that we need to invest in x1, x2, xd for a fixed joint distribution. And we need to do that. But then what we can observe is that if we minimize the cost, same idea as the two-dimensional case, it means that the covariance between x1, x2, xd, the sum, is minimized when you look at this covariance with psi t. And so what we're going to try is to construct a dependent structure between x1, x2, xd, such that when you sum, so the right distribution G, that we need to have the right distribution, but we need to have the right copula with psi, such that the sum of them is antimonotonic with psi. And numerically, this is actually trivial to do. So when I say numerically, it means that we're going to do an approximation. So psi t is not anymore a continuous distribution. It's actually discretized. And I'm assuming that psi t takes only n values. I'm in a discrete market. I have my n states that are given by psi t. And I'm assuming that I have n realization of the joint distribution x1, x2, xd. And I'm putting the n realization in a matrix. So each row is x11, x12, x1d, is one realization of the vector. And I put n realization independent of this joint vector. And so you could see that as a discretized version of the joint distribution of x1, x2, xd. And so, or a discretized copula. So this is a discrete copula, for instance, if you normalize them with the, you take the rank instead of their values, you will directly get the copula from there. But this gives you really the joint distribution of x1, x2, xd in the last d columns. The sum can easily be calculated. You just sum the rows, in fact, the black numbers in each row. And so these are the SI. And then what you do, you reorganize the sample so that when the sum are exactly, the biggest sum is going to be in the first row, and the smallest sum is going to be in the last row, because psi tn is the biggest value. So you just flip the rows so that at the end you get exactly the sum anti-monotonic with psi, and this means that your covariance between the sum and psi is minimized, and therefore you're actually, what you're doing, because you flip the row altogether, you keep the joint distribution. The joint distribution doesn't change, but the price is actually minimum. The covariance between psi t and the sum is minimum. So the joint distribution, you really have to see each row as a realization. So if you don't exchange numbers within one column only, then you would perturbate the joint distribution. But if you do just flip the row, you don't perturbate the joint distribution. You really just perturbate the order in which you observe this realization. And then what happens is like you get, in fact, the joint distribution of psi t, x1, x2, xd. And this is actually everything you need to know to construct this multivariate cost-efficient strategy, because now the x1, x2, xd extracted from this matrix is multivariate cost-efficient. So in the multivariate normal distribution, what we can show is that this optimal, that minimize the cost, and at the same time stay a multivariate Gaussian with given correlation. So you fix the correlation matrix, you fix the mu, the sigma, your multivariate distribution is fixed, but you want that the sum of them is negatively correlated with log psi t. And this is possible, in fact, just by constructing a multivariate distribution such that you get this correlation. So AI and AI are explicit. So they are not on the slide, but you can compute them explicitly. And you have, in fact, by the construction, you even have that the sum of xi star is equal to this. And the construction is done explicitly in the Black-Scholes market. So it's a constructive way to do it. So you have the strategy that generates actually exactly a multivariate cost-efficient payoff. And there's no unique strategy, in fact, but it is multivariate cost-efficient at the end. It has the minimum cost. And so numerically, what we did is like, because we had this result and we were able to prove that this is a multivariate cost-efficient payoff, we could actually just verify that our numerical procedure works. And so what we did is simulating from a d-dimensional multivariate Gaussian distribution, and then applying this flipping of rows. And once we have flipped the row and the sums are anti-monotonic, then we look at the dependence between psi t and x1, psi t and x2, and so on, just to verify, for instance, that x1 and the log psi t, the A1, the theoretical A1 is minus 0.71. And actually the numerical one that we find is also minus 0.71. If you want, you can go as accurate as you want, because you can just, this is a procedure that doesn't require time. In fact, it's just the simulation time. If you want 10,000 simulation, you can also do 10 million simulation, and you will just get the A1 that is more accurate and closer to the theoretical one. And of course, you have the correct joint distribution. And if you sum them, this x1, x2, x3, not only it's a multivariate Gaussian, so this, the three first plots are just x1, x2, x1, x3, x2, x3. And we see it's like a multivariate Gaussian. I mean, we see, I can tell you, and then it looks Gaussian, but we need some to test it. But then when you sum x1 plus x2 plus x3, the sum of them, so the sum of the points in the first three panels, will actually be completely anti-monotonic with the log of psi. So psi and the sum are negatively correlated, as negatively correlated as possible. And it turns out that it's even linear in log psi t. But the dependence between psi and x1 is not trivial. It's also a Gaussian, in fact. So this is what we find. So this actually kind of validates our discrete procedure and made comfortable that any distribution that we don't know the explicit expression of the cost-efficient strategy, we could actually construct it immediately using the numerical setting as soon as you're able to simulate from this distribution. Now, why multivariate cost efficiency can be useful? So we went back to a problem that first I will present without the market, and then I will come back to the problem with the market, because that's how we can use the construction that I just mentioned. So if you think about multivariate risk sharing without a market, so you have a variable, a random variable S, your risk. You have D persons, and these D people wants to share the risk. So the sum of the risks is equal to S. And assume that you know what is the optimal way of sharing. So out of all the sharing rules between the D person, one of them is maximizing this function. So this is a problem that is solved, like there's the inf-convolution problem that has been solved several times with, that is related, in fact, that has been solved with risk measures. But you can also do the supremum expected utility, which has been solved, for instance, by Bosch in 1962. So many people have looked at this problem without a financial market. And for some special cases, we know how to solve it. And for now, we have only 2 examples, but hopefully we'll find more by digging in the literature. We know explicitly how to solve this problem without a market. And now what we want is to solve actually the financial problem, where not only you want the sum to be, actually you don't want to be equal to S. What you want is like you have a joint budget and you want your sum to have the right price. That's what matters to you. And so the problem that we want to solve is actually this one, the supremum for some preferences in D dimension with a given budget for my total budget allocated. What I know is that if I find an optimum, it is multivariate cost efficient. And so the sum is anti-monotonic with psi, which means I can write it down this way: fs minus 1 minus f psi of psi t. Fs being the CDF of the sum. So I take my optimal solution, the sum of them has a certain distribution Fs, and I want it to be as negatively correlated as I can with psi. So actually the sum of xi star must be written of this form. So this is what we've done in some sense with this multivariate cost efficient setting. We cannot express x1 star directly as a function of xi t. This is the difficult part, but we can express the sum of xi star directly as a function of xi t, because as a function of the sum, then it's like the univariate case. It's just the only variable that is distributed like the sum, and that is as negatively correlated as possible with psi. And now from there, so we know this sum must be of this form. And we know that if the sum is given, we can solve this problem. So this is a problem without the financial market. If I know the sum, I know the solution of this can be written as y1s, y2s, yds. So for instance, if you have an exponential utility and you're maximizing an exponential utility, you'll find a linear sharing rule. Everybody's going to take a percentage of s. And so x1 will receive a1 of s plus a constant. And xd is going to receive a percentage of s plus a constant. And the only constraint is that the sum of xi needs to be equal to s. The problem is, when you look at this problem, you actually don't know S. S is not given. So the problem of solving this, if you know how to solve the risk sharing problem without the financial market, you can solve the risk sharing problem with the market thanks to the quantile formulation. Simply because your sum is written this way, and you know that x1 at the optimum is a function of the sum, is this y1s, y2s, yds. So this is the optimum when I give the sum. And here I have that the sum must be of this form. And so at the end, I can actually write down the problem this way. And now I have a quantile formulation. I have the quantile of the sum, which is my unknown. Y1, yd are given, and in some special case are known. And then ut is the same as before, 1 minus xi of xi t. And this is an optimization. It looks more complicated, but actually it's just a function of the quantile of S. So it's as complicated as a univariate problem, because the only unknown at the end in this setting is what is the sum you want to share? What is the distribution of the sum you want to share? And if you find the distribution of the sum, then you actually find everything thanks to the previous setting. And so then what we did is trying to do it in exploit this observation with an example, and we do it with a discretization again. So we discretize the problem for xi t, and we assume it takes n values. We formalize the problem of maximizing the d-dimensional problem as a maximization in a discrete setting. So maybe I should write it this way. So here, I'm looking directly at this problem. This problem, I want to solve for a quantile. A quantile function in the discrete world is just the n values the variable takes. Because if you know the n values that the variable takes, you actually have the quantile function. That's the empirical quantile function. So I'm going to solve this problem numerically, which means this whole big function is a function of S1, S2, Sn. If I discretize the problem, there's n values, xi1, xi2, xn. And what I want to know is what is the value of S for when xi is equal to xi1? What is the value of S when xi is equal to xi2, and so on? So I formulate the whole problem as this one, a maximization of a S1, S2, Sn, which is my quantile function, in fact, over an admissible set. And the admissible set says that you just need to satisfy the right budget. And in addition, we need to exploit the fact that this S1, S2, Sn is anti-monotonic with xi. So how to exploit this? So we have this optimization to do. We want to exploit this. So what we do, we replace S1, S2, Sn by the search for Z1, Z2, Zn, where they are all positive now. And we have that Z1 is less than Z1 plus Z2. And so we are looking for the increments. By looking for the increments, we ensure that the sums are increasing. And it's easier to actually, the optimization is much more stable if you're solving on R plus than solving on R. So we actually reformulate the problem this way, and we solve for n values given a budget constraint. The zeta I are also explicit. They are related to the xi I. So it's just a rewriting because the pricing kernel applies to the Z, to the S. And so you need to reformulate it to get the pricing kernel with the Z. And so you solve this this problem, and we did it numerically on an example where we were able to solve it explicitly. So the example where you have an exponential utility function, the sum of two exponential utility functions, you know how to solve it explicitly, and that's the explicit solution in theory. Now, what we did is solving it numerically. And so in this case, we know actually that if there's no market and you maximize this joint utility function, your optimum will always be linear in the sum. So of the form A plus BS or minus A plus 1 minus BS. So one person takes 20% of S, the other one takes 80% of S. And then so we we ask the numerical solver to look for which S will solve the original problem, which is the problem that is here. So we want to solve for the financial problem. And we have the theory, we have the numerical solution, they work perfectly. Here, n is equal to 10. If you do 1,000 points and you ask MATLAB or whatever software to solve it for you, it will actually not be very good because a solver with 1,000 unknown, usually it's not good. So the trick is actually to do a very rough discretization, like then find the solution. And once you have the solution, this is a very rough solution, but you can use it as an initial condition for more points. And so every time you just multiply by 2 the number of points, and each time you use as initial condition the previous solution. And by doing that, you can actually manage to get to very big discretization steps and still have your solver doing the right thing and finding the optimum and matching with the theory. So we did several examples and with the bivariate exponential. We have another example, which is the example of inf-convolution of the range value at risk. So I want to explain what is the range value at risk. The only thing that is interesting is that this is the only example for which we find an optimal risk sharing that is not comonotonic. So if you look at the optimal risk sharing, if you maximize your function V, which amounts to minimize, in fact, your sum of risks, you find that the risks are split this way. So this is mutual exclusivity. So S, instead of taking, like if we're like 2 people, we take 20% of S, 80% of S. Now we actually split S in a way where somebody gets S fully if the market goes up, and the other one gets S fully if the market goes down. So we flip a coin and then we decide who's getting S. So it's like mutual exclusivity. One person is going to get it, the other one doesn't have risk at all, and vice versa. It's a complete different way of sharing risks because then the risk is full of like all or nothing. And this is to me, like the kind of opposite, like comonotonicity is kind of the most correlated situation that you could get. Mutual exclusivity can be seen as a least correlated situation because you can never have 2 events happen at the same time, like 2 positive payoffs at the same time. So it's kind of a negative correlation structure. So in this setting, because we know how to solve it explicitly, we can apply actually exactly the same as we did, and we can solve also the minimum joint risk measured as the sum of the risks with a given budget. So this is also, the financial problem can also be solved following our methodology and can be solved numerically without any problem. So let me say a few words on our open questions and where we struggle. Our original problem was maximizing a function v x1, x2, xd with a given budget. And we were thinking, okay, how can we choose v such that the optimal allocation exists, but is not comonotonic? Because we wanted to solve it, to use it as a solution, for instance, for a regulator who wants to optimize, to choose some taxation rules so that at the end, all financial institutions don't go bankrupt at the same time. Or if you are investing in several markets, you don't want to lose money always at the same time, like all your portfolios are comonotonic is bad because you always lose. When you lose in one portfolio, you lose in all portfolios. So actually comonotonicity has many disadvantages, and we wanted to find a function v, like an objective function, where it's not comonotonic. And so trying to find preferences that would not lead to comonotonic allocation, and for which we can solve this problem explicitly. We haven't found much solution, in fact, for now. the only example I have is this inf-convolution with the RVAR, the quantile-based inf-convolution. So if you take supermodular preferences, like many people do, like if you take the sum of utility, for instance, and they are concave, the sum of utility will end up being supermodular. And in this case, all the solution can be solved explicitly, and it's actually all comonotonic. So any multivariate utility function that is supermodular, you get commonotonicity for sure. And this we can prove. If it's submodular, we haven't proved it, and we were looking for explicit results. So for instance, the example that were used in the context of systemic risk by Doldy and Fritelli, they propose a utility that is actually submodular, but they don't solve the portfolio problem. And so at the end, they don't go to something that is possibly non-comonotonic, but we don't have explicit solution. And submodularity is something that is desired when you look at multivariate preferences, also because of the concept of correlation aversion. So people in economics have tried to motivate why, in general, individuals prefer utilities that are submodular than supermodular. And it's simply because you like to disentangle the losses and the gains. So if you're going to lose, you have possibility to lose in your wealth and to be healthy or not. You prefer to lose when you're healthy and to gain when you're sick. So it's like you don't want to have two bad outcomes at the same time, two good outcomes. So you try to hedge them with the different dimensions. And this can only be, this actually says that your preferences are submodular. To avoid commonotonicity, we found that you can do quantile-based risk sharing, but then this is the extreme case. And for a regulator, if he's regulating the market, getting the optimal quantile-based risk sharing with the split that was proposed, that is optimal risk sharing, means that you never have one bank, two banks cannot go bankrupt at the same time. They always go bankrupt in different states, and sometimes they get a loss in different states. It's not very realistic to think. Now it would be good, of course, but it's really an extreme negative dependence. Or you go with multivariate cost efficiency. And so that's our kind of message. We think that multivariate cost efficiency can be used as an objective function to optimize. So if you don't know which utility to use, then you can use multivariate cost efficiency, because then you choose which distribution you get at the end. And because you choose your desired distribution, you can choose something that is not comonotonic, and you don't have to choose something that is extremely negative. You can choose something that is in between, that is just less correlated, something Gaussian with correlation 0.2, and you can impose this, and you can actually take it as your objective. You choose your portfolio. So that is the cheapest way to obtain a joint distribution that is the one that you want. And we think that this can be used as an objective for collective decision making. That will be, for me, much smarter than choosing a utility and optimizing a joint multivariate utility. Because if you optimize the joint multivariate utility, chances are that you're going to get to a comonotonic situation. And then we always have the problem is that choosing a utility is super hard. So people have shown, and even in one dimension, that it's easier to choose the distribution than choosing the utility. So our thing is that in one dimension, if you give me the distribution, your desired distribution, I can give you the utility function that you can optimize. And then you optimize your utility function, and then your xt star, your optimum, will have the right distribution. And what is nice is that there's a bijection between the utility function that are concave, non-decreasing, and the distributions. So for any distribution, there's a concave utility, and for any concave utility, you get a distribution, of course, like you can solve for an optimum, your optimum has a given distribution. But you can really link the two. And so then it's easy to say, okay, which distribution you want? Okay, then I know which utility I need to optimize. The problem is, can we do that in multivariate setting? For now, we have really, we have tried, and it's not unique for sure. It probably does not exist within the expected utility setting. but we don't have results, in fact. So this is really a complete open question for us. So yeah, this multivariate cost efficiency is kind of a natural extension of cost efficiency. We hope that it has, that I managed to convince you that there are possibilities to apply, that it can be used for improving a multivariate optimal allocation. So you can take your portfolio that you've chosen and then look at its joint distribution, and actually you can find a cheaper, maybe if it's not multivariate cost efficient, you can actually find a cheaper portfolio that will give you the same joint distribution. That's a way to improve allocation. Or it's a way to design an objective function to ensure that your optimal strategy has the dependence that you want. And so maybe a smart way to collectively invest together. And we're working more in the cost efficiency, not multivariate cost efficiency setting, but on extending cost efficiency with incomplete markets. And very soon, I think Stefan and I will actually release something on incomplete markets. And then we already have a working paper with Jérôme Junique, Thibault Lux, and Steven on cost efficiency and ambiguity when you're not sure about your distribution function F. But there's still a lot of open questions and problems. So thank you very much. And I'm happy to answer any questions you may have. Here are a few of the citations I have, but I realized they were not all the references were not there, but yeah, it was too late when I saw that. So I'll stop here.
Perfect. Thank you very much, Carole, for this very interesting talk. I've seen there's one question in the chat by Harvey Stein. Would you like to ask the question?
Sure.
Directly?
Yeah, going back a few slides, you had the formulas up a little earlier. Oh no, the last one where you had the two formulas, right?
For the exponential utility or for
the general model? No, it's towards the end. It's like one of the last few slides.
You mean this one?
I was looking at past there. Keep going. Yeah, that's go back. Yeah, just one.
Okay.
Yeah, so you're maximizing this V function conditioned on this expectation being less than W, right? So if you don't have a relationship between V and V in some sense being monotonic with respect to this expectation, right? Then it's not going to be the case that the maximum is necessarily around the border, right? Around the right where the expectation is equal to W0. So then you kind of have these intersection of two level sets. So it could be the solutions could be kind of all over the place, right?
So what if you are increasing in at least one dimension, then your budget will be binding.
But you need it increasing in one dimension for all values of the other one, right?
At least, yeah, you need to be increasing in one dimension. Now, probably the maximum exists.
But then, yeah, but I mean, I'm
increasing
sure
in all dimensions. So what's more natural is just to assume it's increasing in all dimensions. In fact,
Harvey, financially speaking, I think there's an easy answer. Usually, you have a risk-free asset, and if you put just all the money up to the budget constraint in the risk-free asset, and in this way you increase your utility.
Right. Well, I mean, generally speaking, I mean, which is why I was asking about this comonotonicity condition, because I mean, financially speaking, usually more is better, right? In which case, increasing the, getting more in an X is better at all points in the space.
Yeah. Yeah. So most likely,
in which case, which is a constraint on what the shape of V should be, right?
Yeah, I would say naturally your V will be increasing in all dimensions. Like,
right, as long as V is increasing in all dimensions. So that's different from this comonotonicity that you were talking about?
the cumulativity is just the optimum at the end. So the fact that your optimal wealth, your optimal portfolios will be increasing in each dimension. So you could be, I think you could be comonotonic and still have things that are not comonotonic. So if you take the example of the Embrecht, I think this thing will be increasing in all xi, but the optimum, they are not comonotonic because there's one positive and the others are 0. So you don't have the comonotonicity at the optimum.
In this case, is it also the case that the intersection of AI and AJ is null?
Yes, indeed.
So the AI are partition of omega.
Yeah, it's a partition indeed. I didn't say it, but this is a union. The union is the full space, and then the intersection in between two AI are empty sets. So it's really they are mutually exclusive at the optimum.
So this is something that's kind of like the Arrow-Debreu payoffs in the space in a certain sense.
Yes, exactly.
If you were discrete,
kind of yeah, exactly. It's kind of to get this as the optimum. Indeed. You partition S based on a certain number of Arrow-Debreu. Yeah.
There's another question, Ephraim Ekran. Would you like to ask?
Yes. One question, one annoying question. How do you invest in the stochastic discount factor? Like practically, it's a practical question. Like how do you invest on, how do you buy XIT or sell XIT?
You mean this thing like XIT -1?
No, not the distribution, the random variable XIT, right?
How do you get it?
Yeah.
You get
how do you invest on it? How do you buy it?
You take the Black-Scholes model and the XIT is linked to the stock price. So then you just. So yeah, my setting is in a complete market. So XIT is directly linked to your risky asset in fact, because of completeness. And so because you have the link between, so then it's not a problem indeed. But in incomplete market, this could be a problem indeed.
Okay, thank you.
Thank you. We have another question in the chat. Any ideas on the generalization when T is random, capital T?
No, we haven't thought at all about it. When capital T is random, I think Stefan can answer. He did something with stopping time in this direction.
Well, I did something with stopping times, but this is basically, I can say something about the case when you want to sell something at a random time.
Yeah, but so your horizon is random.
We have a random time horizon, but we try to optimize over the time horizon and not that the time horizon is given.
Yeah, that's true. That's true. But yeah, I haven't thought about it at all. So yeah, please feel free to work on it. Yeah, I'll be happy to help if you have questions and need more explanations on something I've done, but this I haven't done.
Thank you. I think there's another question by Ephraim. Or was it an oversend? No.
Yeah, about this cost efficiency part, I mean, do you have a paper out on that, or are you writing it?
You mean this, the very first problem? Yeah.
Multidimensional cost efficiency problem.
We have like this is we have the paper, and I think it is already, there's a version online. So this one I think is already posted online, and this has the multivariate cost efficient problem.
Okay, thank you very much.
Stefan, would you like to ask your question?
Yeah, I was wanted to ask if there is a possibility, or if you thought about thinking about multivariate preferences in a set valued sense. So like Birgit Rudloff, Zach Feinstein, and so on, if this would be a potential approach to think on this problem.
I'm not sure I understand But no, I think I haven't done this. I haven't thought about it. Yeah, I'm not sure I understand exactly what you mean.
Okay, we can discuss offline.
But yeah, I think we haven't done it.
Okay, I think there's one more hand. I can currently not see who, if someone wants to unmute themselves and just ask, please.
Hi, but hi, but I would like to ask you is maybe that's maybe this is similarly annoying to the last question that was posed, but is there a way to sort of formulate the problem in any sort of dynamic setting, either discrete or continuous time? Is it at all possible? I mean, the solution would probably have to involve a very different methodology, but have you thought about any possible formulations in a dynamic setting?
No, and yeah, actually, I don't know if there are. I don't think there are many papers who try to do multivariate utility, even expected utility with consumption in a dynamic setting. But yeah, that's probably very challenging. I haven't thought about it. Like it's all without consumption. It's all about terminal wealth, in fact.
Yeah, I mean, that seems to be a gap in portfolio theory in general. Optimization in a dynamic setting is quite limited. But yeah, thank you for this talk. Thank you very much.
You're welcome. Yeah, thank you. Yeah, the dynamic setting. I guess it must be feasible to find more results in this direction, and there must be interesting things to find.
Thank you. Are there any more questions or comments? If not, I guess we can stop the official part. Thank you very much, Carole, for this really very nice talk.